Now, our next character in the study of geology and the development of our science is Giovanni Arduino. He's Italian, and he was one of the top experts on mining and mineralogy back in his day in the 1700s. And he devised a formal subdivision for rocks in Europe. So he's kind of the first one who's starting to think about geologic time and how rocks formed over time. And he decided that you had the primary rocks, and remember, primary would mean first. So the first rocks that we get are igneous and metamorphic rocks. And the secondary rocks are sedimentary rocks, nice solid sedimentary rocks. Tertiary, or the third rocks to form, are basically unconsolidated sediments, unconsolidated material. That's the material you can dig through, right? Like sand and gravel and stuff. And then quaternary, or fourth, were the rocks that we actually watch forming the recent volcanics. And that was his subdivision. He's like, okay, these rocks formed first, these came second, these came third, and these came fourth. And so he's really kind of the first one to start thinking about the timing of when different events occurred in geology. And as we progress through the 1700s, people are starting to think in more and more detail about how our planet became shaped the way it is, why does it look the way it does, and they start to think of why does it work the way it does. So we get to one of the top scientists, top geologists of his day, Abraham Gottlob Werner. And he devised this concept in geology called Neptunism. Well, first of all, he published this hypothesis of the origin of Earth's crust in 1787. And his Neptunism was, well, it's an interesting idea that he came up with. And Neptune was I think that's the Roman god of the seas. And according to Neptunism, all rocks form from water. All rocks. And so Werner said there was originally a global ocean that covered the entire planet, so it was like water world. And this global ocean has become smaller over time. And like I said, all rocks precipitated from water. And so what he was saying is we had this first sea level all the way up here, and that's where we get our primary rocks, right? Those first rocks precipitate from that. And then sea level drops, and during that drop we get these rocks called he called them the transitional rocks. And then the sea level dropped again and precipitated secondary rocks, and then the sea level dropped to its present level, and as it dropped, it precipitated the tertiary rocks. And so that's the way he broke these things off. And he said these four different rock types all precipitated from water and are left behind as this once global ocean has gotten smaller and smaller over time. Well, I'm just going to pause here a moment and say, I hope some of you guys are sitting there watching this thinking, that doesn't seem right. And in fact, there are some big problems with Neptunism. Well, where'd all the water go? If we had this global ocean once, where did it all disappear to? And then, what about volcanoes and basalt? Like, there are active volcanoes, and we can watch lava cooling and forming and making solid rock that does not involve water. And see, Arduino, he was from Italy, where they have active volcanoes. Werner was from Germany, and while there are volcanic areas in Germany, it wasn't where he lived, and so he just kind of ignored them. So we have these problems with Neptunism. But despite that fact, Neptunism became a very popular idea in science in the late 1700s into the early 1800s. We're going to see a little bit more about that in just a few minutes. Our next character is also from the late 1700s. He lived from 1726 to 1797. His name is James Hutton. He came from Scotland, and he was trained to be, I think, a doctor and a lawyer, and didn't like it, and ended up just living on his estate in the lowlands of Scotland and studying geology. He liked to just look at all the rocks around the countryside. And he was part of something called the Scottish Enlightenment, which were this group of thinkers who was centered around Edinburgh, and were working on things like steam engines and great new ideas of this time period. And James Hutton was a proponent of something called Plutonism that we'll get into in just a moment. But basically, as he wandered his estate and the Scottish countryside, he recognized that erosion happens. And so he recognized that erosion happens, which creates sediment, and that sediment then creates new rocks. So he kind of said there's balance in nature, as all things should be. We have erosion in some areas, and we have deposition in others. So there's always going to be rocks that are being destroyed, while there are rocks being created. He said that Earth has internal heat. It's easy to notice that, especially like if you go down in deeper mines, you'll notice that it gets hotter and hotter. So he said Earth has an internal heat source. And he also said Earth is always changing. This again goes back to looking at the countryside and seeing how, well, rivers change course over time and mountains erode over time. But he said this happens, but it happens very slowly. And so oftentimes we don't even notice that this ongoing change is happening because it is so slow. And so this led him to develop something called Uniformitarianism, which is an absolutely vital principle to remember in geology. Uniformitarianism states that the laws that govern nature have operated through all time, and those are unchanging. So the rules that control the way the Earth and the universe works do not change. But the Earth itself can change, right? The mountains can rise and then can get eroded, rivers can change course, sea level can rise and fall, but the rules that govern all of that remain unchanging for eternity. That's an important principle that Hutton came up with. Now, Hutton also came up with this idea of Plutonism. And Pluto is the Roman god of the underworld, and Plutonism refers to that igneous rocks begin molten. They begin as liquid, melted rock that cools and solidifies over time. So this is in direct defiance of the Neptunists who said, no, 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 every rock out there precipitated from water. Well, that's going to become a battle in a little while. But before we get to the Plutonism, Neptunism rumble, let's talk about another gentleman, again from Britain. This guy is from England, though, and his name is William Smith. And William Smith actually gave us the idea of drawing geologic maps. He studied a lot of fossils, and he worked quite a bit with stratigraphy. And he was, in England at this point in time, science was supposed to be the realm of the upper classes. Like, if you were, rich or noble, then you could think about science. But if you're like a working guy, don't think about science. That is not your place. It's very interesting because it was kind of the opposite in continental Europe, where the people who did a lot of the geological sciences were the actual miners and surveyors and working sorts of people. But anyway, very interesting idea at that time. And the problem with poor Will Smith was he was not a nobleman or rich. He was a working man. So a lot of his ideas were kind of ignored for a significant portion of his life. And fortunately, towards the end of his life, he did have some high-ranking friends who ultimately got him the recognition that he deserved for his contributions to science. He was, like I said, a working man. He was a surveyor. He traveled around England surveying property lines, surveying roads and canals and things like that. And as he traveled around and he surveyed, he also paid attention to the different rocks that he saw and the fossils that were captured within those rocks. And after a while of traveling around to different places, he noted that there was a distinct regularity in fossils. Certain rock layers could be recognized by the fossil assemblages, and that there was this like regular order of fossils to it, like fossils that are lower in the stratigraphic sequence were always different from the ones that were higher. He noted these kinds of things. He also drew the first large-scale geologic map. And this is England, Wales, and just the far south of Scotland. And if you compare it to a modern geologic map of the same area, he was like, really, he did a fantastic job. The modern map and his pretty much look about the same. And what he did was he just outlined where different rocks were exposed at Earth's surface. He was the first guy to do that for a large area, for an entire country. And like I say, he worked quite a bit in stratigraphy as well, and he noted the principle of fossil succession, that certain fossils are unique to certain geologic time periods. And here's this hypothetical stratigraphic section. A stratigraphic section is simply where we show the different layers of rock, and this includes the different fossils. You can see different fossils are found in different parts of that section. And what Will Smith actually noted was he could see this stratigraphic section in like Wales, and then he could travel all the way across to like some part of England and note the same sequence of fossils. They always followed the same sequence. And then he also noticed that there were some fossils that become index fossils, because those exist for very short periods of time. So if you find those, you know you're in a very, very small sequence of time. So it kind of helps you date the different rock type, when the different rocks formed. And those were some of the things that Will Smith gave us. All right, now what about Georges Cuvier and catastrophism? Okay, so he lived from the late 1700s into the early 1800s, and he pondered why some species go extinct. So William Smith and his studies showed that fossils exist for certain points, periods of time, and then they disappear, never to be seen again. They go extinct. And Cuvier was like, well, why does this happen? Why would certain organisms go extinct? Well, and he then started studying the different sedimentary rocks that contain fossils, and he noted that some sedimentary rocks show abrupt changes in both rock type and fossil content. So it'd be like there's maybe a sandstone with certain types of fossils, and then right above it we have a limestone with different fossils in it. And so that's a very distinct change between those rock types. So he thought about, well, why would this happen? And so he developed this idea called catastrophism. He said these sudden changes are caused by giant catastrophes that happen on Earth. So like everything's chugging along just fine on the planet, then big catastrophe happens, wipes out a bunch of life, and that's why we have this major change in the fossil content and life. And he kind of had this idea that all life was progressing to the modern perfection. And some of his followers, some of the people who read his work and were taught by him, ended up believing in what's called catastrophism with special creations, where they thought that like this catastrophe happened and then new organisms were specifically created to fill the vacuum, the void left behind. And not quite right. And Cuvier himself did not believe in that. He just believed that these catastrophes happened to kind of wipe out a bunch of organisms and kind of create a cleaner slate so life could progress. And like I said, he kind of believed in this modern perfection, that now life has become perfected and will not progress anymore or something, but which is kind of weird too. But that was his ideas. All right, let's go to Charles Lyell and Uniformitarianism. While Hutton introduced the concept of uniformitarianism, it's really Lyell who was a big proponent of it. One thing I'll say about Hutton is he was a brilliant thinker, but he was not that good of a writer. And this is back in the days where you would let everyone know about your thoughts by publishing things and writing about them. And he was just, his writing was kind of convoluted and confusing and hard to understand. And so even though he kind of came up with uniformitarianism, it was not really popularized until we get to Charles Lyell, because Lyell was a very, very talented writer. He was very good at taking complex ideas and writing about them in a way to make many, many more people understand those complex ideas. And he wrote this book called Principles of Geology that remained really the textbook of geology for much of the 1800s. He was in fact knighted for his scientific contributions by Queen Victoria. Now, he was a proponent, though, of extreme uniformitarianism, which today is called gradualism. So, in his mind, it isn't just that the rules that govern the planet are unchanging. He thought that, like, the rate at which everything happens does not change. So, the amount of volcanic eruptions we get every year, that's going to stay exactly the same. The amount of erosion we get, exactly the same. The rate of sea level rise or fall, exactly the same. It's not going to change. It's all going to stay. And so that's a little bit extreme, right? Extreme uniformitarianism. So let's talk about these debates of the 1800s. We had the Plutonism versus Neptunism, and when I say this was a major debate of the early 1800s, people would get into shouting matches at like scientific gatherings over who was right, the Plutonists or the Neptunists. And I just found this on the internet and I thought it was kind of cute, right? Plutonism versus Neptunism. So who won? Well, eventually Plutonism, and I say won in quotes, because it is recognized that some sedimentary rocks do precipitate from water. Think about your limestones and your evaporites and things like that. Yes, some rocks do, but not all of them, like Neptunism claimed. All right, what about catastrophism versus uniformitarianism? Either Earth is shaped by these slow processes that happen over time, or Earth is shaped by sudden catastrophes. Well, uniformitarianism won. Again, I put it in quotes because not exactly. Do we have catastrophes? Well, yes, we do. We have major volcanic eruptions. We have meteorite impacts. We have all kinds of things like that happening. But is that the only thing that causes change on our planet? No, it's not. So uniformitarianism is correct, but we do have catastrophes. The rates of processes do vary. Sometimes sea level rises faster than others. Sometimes erosion happens faster than other times. Do catastrophic events happen more frequently during some time periods than others? Sure. We know, for instance, that the Cretaceous had a lot more volcanic activity than today. So sometimes you get more catastrophes than others. It's not like a constant rate of that either. So uniformitarianism is what we think of today. Some scientists, some geologists do call it actualism, and what I want you to remember about it is that the laws that govern nature have been uniform through time. And this was something that John Playfair wrote back at Sycamore Point in when he was looking, or he was talking about Sycamore Point, where he went with Hutton at one point in time. And he said, amid all the revolutions of the globe, the economy of nature has been uniform, and her laws are the only things that have resisted the general movement. The rivers and rocks, the seas and the continents have been changed in all their parts, but the laws which direct those changes and the rules to which they are subject have remained invariably the same. I think that's this nice poetic way of saying everything's changing, but the rules that govern the way our planet works. So I'm just going to finish this with a brief review of scientific method, because we're going to use that in some of our labs this semester. Remember, it's important as a scientist to observe. Have your eyes open. You know, don't just walk through life not paying attention. Observe things. Formulate a hypothesis. And in real life, you actually have multiple working hypotheses. You're like, all right, I have this scientific problem. We could explain it this way, or this way. Let's see which one is right. Then you experiment and test your different ideas. You collect data from that experiment. You analyze the data and think about what does it fit. And then you evaluate and you interpret the results. And so what you might be able to do is be like, this hypothesis was right, the others were wrong, or you might be like, every one of them was wrong, but this was kind of the rightest. So let's modify that to fit what the data is telling us, and then let's do another experiment. Now in geology, we don't always experiment. We often have to look in the rocks or wait for a natural phenomenon to happen. But in some cases, you can go to the lab and do experiments. And so just remember, scientific method is a lot of experimenting, it's a lot of observing, it's a lot of thinking about what the information that we're gathering means to us. And we will have some fun doing that, hopefully we'll have some fun doing that in our labs this semester. And that brings me to the random picture of the day. This is L'Anse Meadow in Newfoundland. This is a reconstructed Viking village. Around 1000 AD, a settlement of Vikings developed there. They built a bunch of houses like this longhouse. They had smithies there for making tools and weapons, and just hung out there for a while, and then eventually decided to go home. So anyway, L'Anse Meadow, me being a Viking, I just think it's an awesome place to visit. Those were the first Europeans, by the way, to settle in North America.